It gives me great pleasure to introduce our speaker today, Professor Anna Scaife. Anna was previously a PhD student and postdoc here at Cambridge, followed by stints in Dublin and Southampton. She moved to Manchester, where she's currently the Professor of Radio Astronomy. She's head of the Jodrell Bank Interferometry Centre for Excellence and the academic co-director of policy at Manchester. In 2014, Anna was honoured by the World Economic Forum as one of 30 scientists under the age of 40, selected for her contributions to advancing the frontiers of science, engineering, technology in areas of high societal impact. In 2017, she was awarded the Blau Chair of Astrophysics at the University of Groningen and was the 2019 recipient of the Jackson-Wilt Medal for the Royal Astronomical Society. As if that wasn't enough, Anna runs training programs to provide bursaries for students in Southern Africa and Latin America, and that's to pursue graduate data science degrees in the UK. As we'll hear today, her research is focused on using AI as a discovery tool in data and intensive astrophysics. She's led a number of projects in the area of technical radio astronomy development and scientific computing, and these feed into the Square Kilometre Array project, including the design of a regional data centre for SKA in Europe. So without further delay, it gives me great pleasure to hand over to Anna to hear about AI as a tool for astronomy in the SKA era.
Okay, thank you very much, David, for the nice introduction, and thank you very much for the invitation to talk today. I'm going to be talking about AI for astronomy in the era of the Square Kilometre Array. So my talk is going to start off by describing the SKA, in case there's the vague possibility that there's someone in the audience who hasn't heard of it yet, and then I'm going to basically motivate why machine learning and AI are important for the SKA as they are for many other astronomical observatories these days. And then I'm going to talk about some of the work we've been doing understanding uncertainty and bias quantification in the use of AI for astrophysics, and specifically in radio astronomy. And I'm going to use the example of radio galaxy classification, not because it's the only example, but because it's a pretty canonical one that I think is quite accessible. But of course, there are many, many other applications of AI across radio astronomy and astrophysics more broadly. So to start with, the Square Kilometre Array is going to be the world's largest radio observatory. It's in fact two telescopes, the first of which looks like this. This is the mid-frequency array, which works in the centimetre wave regime. And this is a dish-based radio interferometer, which would be primarily focused in the northern Cape of South Africa. But the 197 dishes of phase one of this array will actually stretch out over about 200 kilometres out from the northern Cape up to the borders of Namibia and Botswana. This is the first telescope. Obviously, radio astronomy covers a very wide range of wavelengths. So the second telescope, which works at meter wave frequencies, looks quite different. Anyone who's familiar with the LOFAR telescope will probably see the similarities here. So this is the SKA-1 low telescope, which is a dipole-based radio interferometer with the dipoles beam-formed, so electronically phased into stations that operate essentially in the same way that dishes do in the mid-frequency interferometer, and then all of those stations form, again, a radio interferometer. The baselines here are shorter because of the science case for this array, which primarily revolves around detecting the epoch of reionization. But in terms of antennas on the ground, phase one of SKA-1 low will put about 130,000 of these dipoles onto the ground in Western Australia, which is one of the most radio quiet areas in the world, and therefore ideal for meter wave radio astronomy. So as I said, the two arrays use different technologies and cover different parts of the radio wavebands in order to address the breadth of science that the SKA aims to look at. And these are really the drivers for the technical specifications of the telescope. So again, I'm not going to go through everything, but just to highlight some of the key science drivers for the SKA Of course, detection of the epoch of reionization using meter wave observations of the shifted 21 centimeter line are the primary driver for the low frequency array, not just detecting the redshift at which the epoch of reionization occurred, but also mapping out how it occurred in order to separate between different potential progenitors of ionization in the universe. In the time domain, the use of populations of pulsars across the Milky Way is going to be used to constrain the passage of gravitational waves, giving us a completely different window into gravitational wave astrophysics than, for example, the LIGO experiment currently gives us. So the SKA will probe a much higher mass regime than LIGO currently probes, and will give us a much more visual picture of how gravitational waves propagate through our galaxy. One of the most popular science cases amongst the public is, of course, the search for extraterrestrial life. And like pretty much all modern radio telescopes, the SKA will operate with very high spectral resolution. And so looking particularly for molecular traces of life on other planets is another key science goal. And then last but not least, because it's my favorite science case, is using all-sky surveys of polarized radio sources to differentiate between different origins for cosmic magnetic fields is another key driver. So this is distinguishing between magnetic fields that were formed in the very early universe and then amplified through structure formation, and distinguishing those from the contributions that might have come later through the action of injection of magnetic fields by jets and outflows from radio galaxies, for example. So this is the science that drives the experiment. I'm not really going to talk about the science in detail today. Really what I'm going to talk about is how we handle the data that allows us to do that science. Because the SKA is not just an astronomical observatory, it's also a big data machine in really the truest sense of the word. So if you take the two telescopes in South Africa and Australia, each of these instruments has an output data rate of about 10 terabits per second. And that is actually significantly smaller than the raw data rate in the low frequency array, which is quite staggering. That 10 terabits a second goes through a number of processing stages within the observatory and gets compressed down into a mere 300 petabytes per year per telescope, so 600 petabytes a year combined, and that's what the radio astronomy community will be dealt, essentially, and sort of told to get on with it and do some science. But of course, it's a huge amount of data, and it makes even the most basic processing that we do extremely difficult to do in what would be considered a reasonable, timely fashion. And so, of course, all of these things together have led to a significant interest in the development of automation of a lot of the processing that these days we might do by eye or through the action of grad students. So the things that I'm talking about are, object identification, object classification, cataloging, comparing different fields, all of those things that normally, we probably wouldn't even really think about too much, become extremely difficult when you're working with images that are petabyte size, because the size of an average image is probably going to be about, or average data cube, I should say, is probably going to be about half a petabyte, which is quite staggering if you compare it even to the large data sets that we're getting today from the LOFAR or the Meerkat telescopes. And the community is, aware of this and has been looking at ways of doing these things in an automated fashion. And of course, these days, an automated fashion means machine learning or deep learning or artificial intelligence more generally. And you can see that reflected in the number of papers that are being published on the archive that include those keywords, either in their abstract or title. You can see the massive increase, perhaps since 2010, the huge number of papers, especially that reference different machine learning methods in astronomy, has grown enormously. And of course, this isn't specific to radio astronomy, because other astronomical observatories are also experiencing huge data explosions, as is, of course, other fields within the wider scientific community. Particle physics with CERN Run 3 and Run 4 have a similar big data problem that they're also looking to address. So, just to give an example of where this might be needed, here's a survey field from the LOFAR LOTS survey. So this is a radio survey at meter wavelengths from the LOFAR telescope. For anyone who's familiar with LOFAR, this is part of the HEPDEX field. And as you can see, there's a large number of objects detected in this field. For anyone who's not a radio astronomer and doesn't really know what they're looking at, basically every bright point is a supermassive black hole. It's a radio galaxy or an AGN. And a lot of the analysis that will be done with the LOFAR surveys is population analysis. So we need to be able to extract all of the objects from these surveys, catalogue them and form them into different populations, different types of objects. And then more importantly, we need to be able to identify what's new, what wasn't, what isn't part of our known population. Because history tells us that every time a new astronomical observatory is built or put into operation, the thing that it generally becomes famous for is not the science that it was designed to do, but the discoveries that it made. And so separating out new discoveries from known populations has always been important in astronomy. And as we automate the processes that extract our objects from our data, we need to be very careful not to automate out that potential for discovery, because otherwise we significantly limit the potential of our investment in astronomical observatories. So one example of populations that we might extract from, say, the LOFAR fields, and this is an active example because people are doing it at the moment, is to separate out different types of radio galaxy. So I've just highlighted a couple of little radio galaxies here. So again, radio galaxies are typically supermassive black holes that are ejecting jets of relativistic material into their surrounding medium in order to conserve angular momentum. And we tend to classify these in different ways, but primarily morphologically. So you can see that these two radio galaxies look really quite different. And again, I'll talk about this more in the next couple of slides. But from a machine learning or an AI point of view, if we're talking about morphologically classifying objects like these radio galaxies, what we're really talking about is the application of convolutional neural networks to astronomical data. And so that's what you can see here at the bottom right. This is an example of a convolutional neural network used for classifying radio galaxies. This is actually a specific type of model that uses a technique called attention gating to identify what the model is looking at in the image to make its classification. So the morphological classification that we might make on the very simplest level would be to classify radio galaxies into Fanneroff-Riley class 1 and class 2 sources. So there's a couple of examples here on the left. So a Fanneroff-Riley class 1 radio galaxy typically has two visible jets. The jets aren't particularly collimated, and they tend to just sort of fade away like smoke from a chimney, like a Kelvin-Helmholtz instability, into the surrounding medium. A Fanneroff class 2 source looks somewhat different. The jets are typically highly collimated. We typically only see one of them due to relativistic boosting, and then they are terminated by termination shocks where the jet is impacting on the surrounding medium. And this is a classification that's been around since the 1970s, but it's one that persists to today. So It's a standard classification scheme, but it's also one that has become more difficult to understand as time has gone on, because the original morphological distinction seemed to be governed by basically a luminosity threshold, so it could be attributed to the power associated with the jets. These days, we see from more recent radio surveys with better resolution, better sensitivity, that in fact that luminosity distinction is not quite so clear. And that's what you can see in this figure here. So this is from the LOFAR lots survey, and it's showing you, well, size of the radio galaxy, projected size of the radio galaxy against the luminosity is 150 megahertz. And you can see that this dividing line between the FR2 galaxies in blue and the FR1 galaxies in yellow is really not a great distinction. There's a lot of overlap between these two populations now. And this, results in scientific questions again about what is causing this morphological difference. Is it something to do with the jet dynamics? Is it to do with the mode of accretion onto the central black hole? Is it intrinsic to the central engine of the galaxy, if you like? Or is it connected to the local environment? And then the environmental question can become one of local environment of the surrounding medium or the composition of the jets. So, for example, what is the exact makeup of the jets? Is it electron-positron, electron-proton? Is that material intrinsic to the jets, or has it been entrained through the motion of the jets through the surrounding medium? So these are still all essentially open questions that have in some ways become even more confusing as we get more data, because the distinctions become less and less clear. So for the LOFAR lots survey, these populations had to be extracted from the survey, just as they will be for the new telescopes that are coming online. And historically, this is something that's been done predominantly by eye, by people looking at images of radio galaxies. And that's been manageable because of the number of radio galaxies that you would typically see in a survey. So the NVSS and FIRST surveys from the VLA telescope in the 1990s, they detected somewhere between 50 and 100 radio galaxies per square degree on the sky. And you can see a little selection of different radio galaxy postage stamps there on the right-hand side. The LOFAR surveys detect about 1,000 sources per square degree. And as we go towards the SKA, the Australian SKA Pathfinder telescope is going to detect about 3,000 sources per square degree. You can add in another factor of a few for the Meerkat telescope. And when you get up to the SKA, you're talking somewhere in the region of 10 to 100,000 sources per square degree. And at that point, it's not a by eye problem anymore. And as one of my postdocs likes to say, there may be enough grad students in the world, but there certainly isn't enough coffee in order to do this by eye. And it's just not practical. Some of my students worked out by taking pictures of radio galaxies around the department that an expert radio astronomer takes about a minute per source to classify it as a FR1 or FR2, which means that if that was the only thing you did in your entire job, you'd classify about 125,000 sources per year, which is not enough. Citizen science is another way of approaching these kinds of problems. But of course, as you open up the problem to non-experts, you need a higher level of consensus in order to classify any individual object. So for example, the Radio Galaxy Zoo project classified about 300,000 sources with the help of 12,000 users over about 5 years, which is a lot of sources, but also doesn't scale to SKA survey speeds. And then, of course, you can build a machine learning classifier, and then you can classify about 100 million sources in about 15 minutes. So that's when it really starts to look very interesting in terms of replacing what was essentially manual astronomy labor in the past. So there's a great interest or optimism about the use of AI for astrophysics. But of course, some of the problems that are faced when you're using astrophysical data sets are not the same as the problems that were being addressed when standard computer science machine learning algorithms were developed. So one of the things that is quite challenging in astronomy is that even though we have very large archival databases and surveys, we only have a small number of labeled data sets. So for any kind of supervised learning problem, so where we're trying to separate something that we know into discrete classes already, even though we have too much data, we also have not enough data. It's a nice paradox to be working under. The other thing that astronomy has, along with a lot of other scientific fields, is that our data have very significant and variable class imbalances. And what I mean by that is that there are not equal numbers of all of the different classifications in our data. So if we looked at a survey of radio galaxies, we might find that there were predominantly more FR2 sources than FR1, say 60% FR2 and 40% FR1, which is not a massive imbalance. But if we were trying to separate, for example, pulsar candidates from RFI signals, we'd find that we had about one real pulsar for every 100 RFI signals if our data were clean. If we didn't clean our data, it would be more like 1 to 100,000. So that's a huge class imbalance, and that affects the way that AI works. The other thing that is not done as standard in most applications of AI, even today, is that although our model will make a prediction, it doesn't tell us how confident it is in that prediction. So AI doesn't natively provide any uncertainty on the predictions that it makes, and it certainly doesn't calibrate those uncertainties in a way that we would recognize as scientists. And then the final point is that when we introduce an AI model into our analysis, that model is going to be subject to the same kind of selection biases that our instruments are. So we need to be able to quantify the selection biases that arise from our use of AI in exactly the same way that we quantify selection biases from experimental or observational data recording. So these are the questions that I really want to focus on in this talk, because these are the questions that we've been thinking about a lot recently. But just before I dive into how we're doing that, I apologize to anyone in the audience who already knows about neural networks and deep learning, but for those who don't, I'm just going to give a very, very brief intro so that people know what I'm talking about as I go forward. So the way that a typical neural network classifier works is quite straightforward. You put in an input data sample at one end, and you get out a pseudo probability for your target classes at the other end. And that pseudo probability is constructed through the action of what are referred to as neurons that exist within layers between the input and output layer. And each of those neurons is mathematically quite straightforward. It applies a set of weights to your input data and then a bias to give you an offset. So these are the learnable parameters of your model, the weights and the biases. And so when you train an AI model, that's what you're doing. You're learning those parameters. And you learn those parameters for every neuron in your model. Typically, each of these layers of neurons is followed by a non-linear function in order to maintain the independence of the layers, so that you don't get degenerate solutions between your weights and your biases. And the way that you train the model is that you pass some data through the model, you get an output, and you evaluate how good that output is by comparing it to an input label on some known piece of data. So for example, if I wanted to know if this radio galaxy was an FR1 or an FR2, I would assign one of my outputs to be FR1, one to be FR2, and then I would compare my output pseudo probabilities with a label that I knew a priori because some expert had labeled my data sample for me. And I would do that comparison using a cost or a loss function. And then I would back propagate the gradient of that loss function with respect to each of my trainable parameters, each of my learnable parameters through the model, and update those parameters according to that gradient. And that's a process known as backpropagation. And so the training process is iterative. We do this multiple times for multiple pieces of data until we find no further improvement in our loss function. And then we say the model is trained and we can pass some new data through it that hopefully should give us the same kind of outcomes. So this is what's known as a neural network. It's also called an artificial neural network. It's called a multi-layer perceptron, a fully connected network, or a feed-forward neural network. They all mean the same thing. The difference between this and a convolutional neural network is that in a convolutional neural network, we will have some convolutional layers at the beginning of the model, which basically have shared weights that learn the value of a convolution kernel that's applied to the image, and that enforces translational equivariance, which means that our object of interest doesn't need to be in the center of our image every time. And it reduces the total number of learnable parameters that you need in your model. So from this, basically what I want you to take away is that you put an image in and you get out a probability, pseudo probability, of that image being one of n classes, where in my example, I have 2 classes for 2 types of radio galaxy. We call these, people will refer to them as probabilities. Typically, the output of the model is an unnormalized output, and we pass it through what's called a softmax function, which normalizes it into the range 0 to 1, with the outputs all summing to 1, so it becomes like a probability function. And so we can visualize the output as being 0.1 and 0.9 for this particular image. So in this example, this image, the model is saying that it's 90% probable that this is a FR1 type radio galaxy. And that's fine. Essentially what's happening here is that we're learning the maximum likelihood solution for the model. If we want an uncertainty on our output, which is really what we want to know, because we want to know if I perturb my model very, very slightly, is it still going to give me the same result? What we need to do is we need to calculate the maximum a posteriori value and get a distribution over these 2 sets of outputs. So there are different ways of doing that. It's not an unsolved problem. The first and most common way of doing it is to use something called dropout. Now, dropout is a method that iteratively removes neurons from your model with each pass during training and each pass during testing, if you apply it in that way. So this is a sort of a Monte Carlo approach to removing neurons from your model. And it was introduced first to avoid models relying overly on individual neurons within the architecture. But it's since been shown to give you a posterior probability distribution, which I'll talk about a bit more in the next couple of slides. So if we apply dropout in our model, especially during test time, and we pass the same image through our model 100 times, each of those 100 passes will have a different realization of neurons removed, and it gives us the distribution of output probabilities for this particular sample. And we can see here that we no longer get just a single line at 0.9. There's some width to it. There's a little bit of overlap in the middle. But in general, it looks like these distributions agree with our single pass of having a mean of about 0.1 and 0.9. A more general approach to this, rather than using dropout, is to use variational inference in the model. So in this case, what we do is we don't just learn the weight and the bias for each neuron. We would parameterize a variational approximation to the posterior on each of those neurons and learn the parameters of that distribution. So for example, I could say that I assume that each of these neurons will have a Gaussian posterior distribution, and I'll learn the mean and the variance of that distribution. So it doubles the number of parameters that you need to learn. But equally, if we then learn those posterior distributions on each of our neurons, we can propagate a sample through those distributions to give us a nice posterior distribution on our output, which again might look something like this. Now, in practice, using variational inference for this problem is a really flexible approach. It has pros and cons. I'm not saying it's perfect, but one of the things that it allows us to do is it allows us to actually define the posterior and in fact the prior that we expect on our weights and our biases in general through the network. And the way it does this is that we optimize a cost function that minimizes the difference between the true posterior, which we don't know, and whatever the variational approximation is that we've chosen. And typically this is done by using a measure in statistics called the KL divergence, which basically measures the distance between two probability distributions. Now, in its most basic form, it's not something we can apply because the true posterior is intractable due to the range of weights and biases that are available to us. But we can reconfigure this minimization objective so that it looks like this line. And this is basically now minimizing the difference between our approximate posterior, which we've defined ourselves as a Gaussian or something else, some prior that again we have control over, and then a likelihood term, which is essentially the same thing we would have used if we were just using a normal neural network. So this term is generally referred to as the data term, and this is the complexity term. The downside of this, of course, is that you have to be able to make a reasonable guess at what your approximate posterior and what your prior distribution are going to look like. I'll talk a bit more about that later in the talk. But the nice thing about this is that it was actually shown quite a long time after dropout started being used as a standard method. That dropout is actually the same as using variational inference, but with a specific choice of prior and variational posterior. So dropout is a specific example of the more general variational inference method. So we can have a look at how this works, specifically for radio galaxy classification. So here I've got two samples. On the top are some FR1 galaxies taken from the first survey with the VLA. On the bottom are some FR2s. You can see that, radio galaxies, there's really a zoo of radio galaxies. They don't all look like they're perfect canonical examples, but they still can be classified. So we've done that using a data set that was put together by Miragai and Best a few years ago. And they labeled all of the galaxies in a data set of about 1,500 radio galaxies as FR1 or FR2. And that's what we're using to train our model. So here I'm showing you an example of 4 radio galaxies where the model we've actually passed each of these images, the same image, through the model 200 times. And the model has predicted exactly the same output each time. So, sorry, it's 0 and 1 is FR1 and FR2. So there are actually 200 data points here, but there's no spread in them because the model is extremely confident in this prediction. And the same goes for all of these 4 galaxies. The same is not true for every galaxy in the set. If we take these 4 galaxies and we pass them through the model 200 times, we get a completely different solution every time. The model really has no idea what these galaxies are, even though it's been trained to predict FR1 and FR2. These 4 galaxies just confuse it completely. And the really worrying thing about this result is that if we had only done a single pass, like you do on a standard neural network, we would still get an answer. And potentially that answer could be 0 probability FR1 and 100% probability FR2. So it could look like the model was really confident in its classification, when actually a very, very small perturbation in the model would lead to a completely different solution. The way that we use these distributions to quantify uncertainty is that we look at the entropy of this distribution. And we do that rather than just taking a variance because of the bounded nature of the softmax outputs. But that variance is very informative for us. So one of the ways we can use it is to look at the bias in the model. And this is an example where I've taken an FR1 radio galaxy, I think this is, or possibly an FR2 given the outputs here. Oh no, sorry, FR1 given the outputs here. And I've rotated it by 20 degrees at a time, and I've put the rotated images through the model. And what you can see is that at its original orientation, we get this nice class separation where there's a little bit of variance, but we can clearly see that the model prefers one class over the other. As we continue to rotate it up to 60 degrees, the model gets completely confused. So even though it could recognize the galaxy at this orientation, it has no idea what it's looking at. And that's really problematic because, of course, the Fanneroff-Riley classification doesn't depend on the orientation of the galaxy. The galaxy could be sideways or upside down, doesn't change what kind of morphology it has. And the reason for this is that although convolution is translationally equivariant, so it doesn't matter where in the image the galaxy is, it's not equivariant to rotation, or in fact equivariant to reflection. So what it means is that our model is extremely biased depending on the orientation of the galaxies that it's being shown. So once we identified this bias, we could look at ways of fixing it. And in this particular case, what we looked at was the use of group equivariant convolutions in our network to preserve that equivariance through to rotation and to reflection. So we did this using discrete equivariance groups. So this is a cyclic equivariance group with a fourth order at fourth order, so 4 levels of rotation. And then this is a dihedral group, which basically means you get the same 4 rotations, but you get a reflection for each one as well. And so when we use this kind of convolution, that's analogous to classifying equivalence groups of radio galaxies rather than just translation groups. And you can see it in the action of the model. So here I've got a little radio galaxy, and it's rotating around. And the output of the convolutional layers looks like this. You can see that it follows the orientation of the original radio galaxy, but it also changes very slightly. And you can see that more distinctly if I reorientate the features at every rotation back to their original orientation. So that's what I mean by the stabilized view here. And what you can see is that the features are actually changing for every orientation of the radio galaxy. And that means that the network is having to classify something different at every orientation. If we introduce a convolution that's equivariant to rotation, then you can see that the stabilized view here gives us the same features for every orientation of the radio galaxy. There's a little bit of fluctuation that you can see, but that's due to the numerical interpolation over the kernel, which is very small. It's only 5 by 5 pixels here. And if we look at the results again from our model, this is the original result that I showed you earlier, where when we rotate the galaxy, it gets very confused in the middle. If we do the same thing using a 16th order dihedral convolution, we maintain this nice degree of separation for every orientation. And that improves the performance of our model, but it also tells us something about our data. And specifically, something that we found quite interesting is that the use of cyclic equivariance disproportionately affects the FR1 galaxy population, whereas to improve the performance for FR2s, we actually have to introduce that dihedral component. So this is the average number of misclassifications, which basically decreases as we increase the level of equivariance. And that's, you can think of dihedral equivariance as basically being immune to chirality in the data. So the other potentially important scientific application for this kind of thing is in chemistry, where you want to classify different types of molecule. We can also just extract the uncertainties on different types of radio galaxies. And as I said, this is done using the entropy of that softmax distribution. So one of the nice things we can do with this is that we can look at the general entropy of the distribution, where we can see that the uncertainties are generally a little bit higher for FR1s compared to FR2s. But we can also divide that uncertainty into the model component of the uncertainty. So that's the epistemic or the reducible part of our uncertainty. So this is the uncertainty that would improve if we gave the model more data. Or the aleatoric or the irreducible data uncertainty. So this is the uncertainty that's inherent in the data itself. And so you can't reduce it just by adding in more of the same data. The other place where we wanted to look at the use of this uncertainty was in identifying different types of object from the ones we were training the model to look for. So whilst we trained our model on FR1 and FR2 type sources, we also tested it on some hybrid radio galaxies. So hybrid radio galaxies, by this definition, have basically like one jet that looks like an FR2 and another jet that looks like an FR1. So they're kind of combinations of FR1s and FR2s. And pleasingly, we found that the hybrid radio galaxies had higher uncertainties by all measures, which will be important for trying to separate out populations of objects that we don't currently contain in our population training data. We also looked at whether the uncertainties agreed with the level of human uncertainty. So this data set, the Mirabayan best data set, also has qualifications on every classification, which says whether the human labelers were confident or uncertain in their labeling. And we can see that the uncertainties that we get from the model follow that, with the confident samples being classified generally with a lower predictive entropy than the uncertain samples. And then the hybrid samples, again, have higher uncertainty than either the confidently or uncertainly classified FR1 and FR2 type galaxies. And then just as a sort of a final note on this, one of the more, I guess, worrying things that we saw here was that in the radio galaxy classification problem that we were looking at, we saw an effect that's known in the machine learning literature as the cold posterior effect, which is an effect where your model performance is improved by down-weighting your complexity term in the Bayesian loss function. So the weighting term is referred to as the temperature, and that's what you can see on this axis. So basically, the further we are to the left here, the more we've down-weighted the complexity term, which is the term that basically makes the learning Bayesian. And so it really raises the question of, should we be treating it as a Bayesian problem if doing that really, if we have to downweight the thing that makes it Bayesian in the first place? The answer, of course, is that we should be treating it as a Bayesian problem, but we should be understanding where this effect comes from. So the literature proposes that there are two possible reasons for this effect. The first is model misspecification, which means we've got our posterior or our prior distributions wrong. And the second is likelihood misspecification, which means that our data isn't distributed in the way that we think it is. So we tried a couple of things to look at which one of these solutions might be affecting us here. The first thing we did was we tried changing the prior that we were imposing on our model, and we saw that if we introduced a Laplacian prior rather than the Gaussian mixture model we used as our base level, we did see some improvement, but it didn't solve the problem. We also used a pack-Bayes approach to generalize over a range of posteriors, and that didn't correct the problem either. So between those two tests, we've kind of concluded that model misspecification is having an effect, but it's not the primary driver for this cold posterior effect. The problem of likelihood misspecification comes from the data. One of the things that's been proposed to cause likelihood misspecification is augmentation of data during the training process, which is a pretty standard approach for a lot of deep learning problems. We didn't actually use any data augmentation in this case because the Bayesian model can work with a smaller volume of training data. We tried introducing some principles data augmentation, so rotations and reflections, which we knew would be fine. That didn't correct our data. It made a very small improvement, but nothing significant. So our current working hypothesis here is that likelihood misspecification is the most dominant factor in the cold posterior effect for this work. But it's not due to data augmentation, it's more likely due to excessive data curation. And what I mean by that is that the labels that we have in our training data are consensus labels. So the experts who labeled the radio galaxies took a consensus of views on each one of them. So we don't have the individual human labels. Say if you have 5 people, we don't have 5 labels, we have the majority opinion. And so we think that that kind of curation is changing the likelihood distribution for our data and causing this likelihood misspecification. And so it really is something that we need to think about in the way that we build the training data sets for using AI certainly in radio galaxy classification, but also more widely in astronomy and astrophysics. If you're interested in any of the statistics behind this, it's all in our recent paper, which was led by my MSc student, Davina Mohan. The other thing, very briefly, is that we looked at the calibration of the uncertainties coming from our model. And we quantified this in terms of what's known as the expected uncertainty calibration error, which is basically a measure that says that if a particular sample has a larger uncertainty, it's more likely to be misclassified. So we should expect to see a correlation between the uncertainty values and the errors. And when we did this for a variety of different priors, we found again that the Laplacian prior was the preferred prior because it minimized that uncertainty calibration error. Now, I'm not saying that the Laplacian prior is the best prior for radio galaxy classification here. I'm simply saying that it was the best out of the ones we tried. So in future, what we're going to be looking at in more detail is how we determine our choices in terms of priors and in fact, in terms of the variational posterior for this kind of Bayesian deep learning. And that's basically everything that I wanted to say. The questions that I'm just putting up here are the same questions that I motivated at the beginning of the talk. I certainly recommend having a go at AI for your problems if you're not using it yet. There's a very low bar to getting involved. One of the things I didn't talk about is that we're also using AI to produce new radio galaxies. If you Google these websites, these are websites where you can generate images of people who don't exist, but just that the deep learning creates for you, or cats, if you prefer. And now we're doing that for radio galaxies for simulating SKA sky surveys. And a very final note for anyone who's working in this area and or on technical astronomy aspects more generally, the RAS has a new journal which is specifically geared to these themes called RASTI, which is the RAS Techniques and Instruments Journal. So this is just a bit of an advertisement for that. And otherwise, I'll leave it there. Thank you very much.
Fantastic. Thank you very much. So I have actually used that face does not exist. It is actually terrifying when you play around with it. Okay, wonderful. So questions for Anna. That was a great talk. those that are on Zoom can send a chat to me if they wish to ask questions, but anyone in the audience? Robin?
I'm afraid this is, that was a wonderful talk, Anna, but it's kind of way above my head, all these techniques and so on. But the sort of dark suspicion comes to me that maybe the concept of FR1 and FR2 is artificial, that they're all cats, if you see what I mean. That it's something that we impose on the data and perhaps isn't really there in the universe. How would you respond to that?
So I would say that I actually completely agree. I think that whilst we've started off by looking at developing AI to reproduce what we as astronomers do already, in fact, what we're just doing is imposing the same subjectivity on an algorithm that we've used ourselves. I think that FR1 and FR2, like many astronomical classifications, have just been imposed historically as useful waypoints on what is really a continuum of underlying astrophysical or physical processes. From an AI perspective, I think that probably going forward, a lot of the scientific power of AI is going to be in using unsupervised or self-supervised algorithms to actually discover new patterns in the data that we haven't seen historically, and that we probably couldn't discover ourselves now, given the volume of data that we'd have to look at. So I completely agree with your point, and I think that we're going to see an evolution that supports that view.
That's a good question, or good point actually, is about really the sort of the unknown. In terms of data mining, obviously you're putting this through models where you well define the sources you're looking for. What happens to the sort of the serendipitous sources that for example, we saw in Galaxy Zoo by human eye? Is that something that you can build as an AI model?
Yeah, so I think this is where we're going really with that separation of the hybrid radio galaxies from the FR1s and FR2s. So for that particular data sample, we know that those are hybrid radio galaxies because they were in the catalogue basically. But what we need is a quantitative way of separating them from the populations that we know, which in this case is the FR1 and FR2. And you can't do that just using the softmax output on a neural network. So these measures of uncertainty that we're developing and calibrating will be really important for determining sort of the uncertainty threshold, if you like, above which we've discovered something new, or that we should go and follow up to determine whether it's something new. And this isn't the only approach to that, I should say, but it's the approach that I particularly like.
Okay, yeah, that is very interesting. I have a question from someone in Zoom. So, Anna, you spoke about the time cost per classification, and there was a question about if you had an estimate of the carbon cost per classification.
So I don't for this one, I have to say. One thing that I would, well, I don't know, I guess it sounds quite defensive, but I'm a great proponent of using the smallest machine learning that you can. I think it's somewhat irresponsible in many ways to use giant deep learning models for problems that can be addressed with relatively simple ones. And if you don't need machine learning, then you shouldn't use it necessarily, because especially neural network and convolutional neural network based models, they tend to require the use of GPUs, which are very power hungry. Although on the other side, the flip side of that, I would say that when we were designing the computing for the SKA science data processor, one of the things that came out in the results, which was not my result, I have to say, so someone else came out with it, is that actually GPUs were more efficient in terms of flops per watt. So if your code is well written, then a GPU is a better choice than a CPU. So in that sense, machine learning might be if you can write it efficiently, it might be a good choice. So yeah, that's a rambling answer that doesn't really address the question, but yeah.
But also in context, presumably the processing of the data in the first place is incredibly intensive, and so it's I don't know, a drop in the ocean, isn't that right?
So in some senses, yeah. So the science data processor for the SKA is approaching half an exaflop, just to get the images out, right? So it's a huge supercomputer. So I think the post-processing is about 10% of that overall, but I don't have a number in my head for exactly what proportion of that the AI might make up.
Okay. Yeah, so it's not quite a drop in the ocean in that case. I'll take a question at the back, and we've got a queue of questions. So earlier you said that we first try to make a difference between FO1 and FO2 at the lunar state, and then we found that it doesn't work so well. I was wondering, now that we have these neural networks that are able to make difference quite well, are they also able to tell us which features they're using? Because it could tell us how human could make a distinction. Could be interesting for theorists.
So I didn't quite catch all of the question, but I think the question was, can the neural networks tell us which features are most influencing their decisions? Is that correct?
That is, yeah.
So the answer is yes. Actually, there are a number of different ways that you can do this. So one of the simplest ways to do it is to use a set of tools that are sort of all bundled under the title of explainable AI or XAI tools. So, for example, things like a tool called GradCam, which looks at the gradients throughout your neural network. One of the approaches that we've been using particularly is this attention gating technique that I mentioned very briefly in passing, where your neural network can actually output a heat map, essentially, with each decision, where the heat map identifies what it was in the input image that most helped it make its decision. And again, this is something we've been doing with radio galaxies. And what we're seeing is that typically the model is using the same things that human classifiers would use, which is the ratio of the distance between the brightest point in the jets to the central supermassive black hole, which is the general definition of FR1 to FR2. And we do that by looking at the radial distribution of the heat in those attention maps. So the short answer is yes, we did have to tune the model to work properly for radio astronomy, that I would say. So we developed our own attention gating and our own attention combination techniques, which are quite similar to what's used in medical image analysis rather than what's used in the sort of basic implementations from computer science.
Okay, good. Question over there.
Yeah, thanks again for the great talk. I had the impression that when you have neural network for classification and say it says it's definitely not A and B and it doesn't look like C, you will still get a kind of strong preference for one category that is like not as strongly excluded as the other ones. So say it's not a hybrid, it is not a type 2, and it only doesn't really fit in FR1, that a human would say, oh, it doesn't fit any of these, and like kind of following up on that question, while the network would still strongly say it fits this category. Is it something like a kind of chi-squared number or something like you would get from other statistical tools that tells you this fits in my classification or this doesn't fit with any of my classifications?
So for a standard neural network, so not the kind of Bayesian neural networks I've been talking about, for a standard neural network, it will always give you just a probability of it being in one of the classes that you've told it to look for. So it will always say it's something. Now, it may be that if you have two classes, it says it's got a 50% probability of being in either. But it won't tell you it's not in either of these classes. It'll say it's either in one of the classes or it's equally likely to be in both. When you calculate the posterior uncertainties, if you do it on the softmax values like we've been doing here, essentially that's a bounded function. So again, our uncertainties will be bounded as well. But there are other ways of implementing those uncertainties that we're also looking at, which are unbounded functions. And so in that case, you could have an infinitely large uncertainty on a value, which would tell you that it's definitely not something in your target classifications. The key is setting up the problem properly.
Excellent. Thank you. I was actually going to ask a very similar question. I'll go to Richard and then we'll finish with Casey. Yeah.
Okay, thanks, Anna. Very nice talk. Learned a few new terms. And back to this green question. In optical astronomy, we've dealt with classification problems, like basic things like star-galaxy separation, ellipticals versus spirals, and so the technique tends to be to use moments, like surface brightness, and that's computationally, you basically get a reduced set of parameters that's quite efficient. And I think you sort of mentioned that later on. Has that been tried for this problem? Because that's computationally faster.
So what you're talking about is sort of extracting numerical features from the images themselves rather than using the image as your input. So I think in the optical, this has been done by a variety of people, including, so I think Chris Consolis used that kind of approach for a lot of his classification work. In radio galaxies, yes, so a lot of the automation has been done by fitting splines to radio galaxies and looking at various ratios. So it has been done, and to be honest, for some of our data sets, that's what we're using for the labels, because that's all we've got. But again, I would say that even in the optical, certainly my impression from the Galaxy Zoo analysis, using, for example, Mike Walmsley's ZooBot, which uses the images directly rather than the elliptical features, has actually been much more powerful. And especially in his recent work that's been looking for anomalies in optical galaxy data sets. So one of the things he's been doing is extracting ring galaxies and things like that. And I think that if you compare the feature extraction to the general sort of morphological deconstruction that neural networks do, there's more flexibility in the general morphological deconstruction because your elliptical features, or however you choose to define them in advance, is going to impose a restriction on your classification afterwards, as will a neural network, but it just won't be as significant, I think, because of the range of parameter space that's available. So I don't know. I mean, you're kind of talking to the wrong person, because I'm heavily biased towards the use of neural networks, but I do think that it's more generally useful, is my impression.
Okay, thanks.
Final question.
Hi, thanks for a nice talk. I might consider myself a Bayesian statistician, so I'm really interested in the kinds of priors you used. For example, you showed that how your classification errors depend on the choice of priors on the weights, and it's your variational approximations, and the justification for using dropout is a variational approximation. So, but if you're going to use an informative prior like Gaussian or Laplace, in a normal application which is outside of deep learning, you might say, well, you should use something which reflects your physical understanding of what this parameter means. But the problem with a deep neural network is that this is a prior on one coefficient inside a neuron among millions of coefficients, and it's very hard to think physically of what that means. And so typically what I've seen in literature is they just can use like a standard Gaussian with unit variance and a mean zero or something like that. And I was curious, these kind of default priors, is this the kind of thing that you use in your GMM or Laplace priors, and do you believe them in some sense, or are there ways to learn them in some sense?
Yeah, so I completely agree. I think this is a really big question: is how do you define the priors in a Bayesian neural network? Because you're right, there is no physical intuition there to guide you. So it might be possible to learn them. I'm not. It seems it's probably somewhat so I have the same impression of the literature as you, that many people just use a variance 1 Gaussian as the prior on their weights. And whether there's so our work suggests that is not the optimal prior for this particular problem, but then how we choose a prior and whether we choose an informative prior, so whether we could choose something that is I'm not quite sure how you would necessarily define an uninformative prior in this case, but I do think it's better to define something, because in the case where you are not specific about defining your priors, there's still a prior going in there. It's just an implicit prior, and so you're not taking account of it in your analysis. So I think it's an open question, really. And I think it's somewhere where there's the potential to do a lot of work, not just in machine learning, but specifically for astronomy. And it's going to interact with all kinds of other aspects of your deep learning. So I think it will interact with the architecture of your network, for example. So there's a, so it's not a definitive answer, but it's something that we're really thinking about. I think the next thing that we were planning to look at were Cauchy priors, and go down that route.
Okay, wonderful. Well, let's thank Anna again for a fantastic talk.